Welcome to Sales and Sale Theory. The intention of this session is to give you a little bit of background on the topic so that you may begin developing a bigger picture of some of the decisions regarding sail handling aboard a traditionally rigged schooner. So, what do we mean by traditionally rigged? This means that the rig design was developed by a particular culture or combination thereof over centuries of trial and error in order to serve a practical purpose. It is a design based on a slow process of evolution with less of the abstract mathematical design calculations of today's modern racing yachts. A schooner is one type of traditional rig, but what makes it a schooner? A couple factors. First is that a schooner must have two or more masts. To be a schooner, she has a mainmast and a foremast. She can have plenty more than two, but in order to be called a schooner, she needs at least a fore and a main. The biggest schooner that ever sailed was the Thomas W. Lawson, built in 1902, and rigged with 7 masts that each had a name. The second factor that determines a ship to be a schooner is that the sails are rigged fore and aft, meaning that the sails, when in the neutral position, run parallel with the keel of the ship. This is opposed to being square rigged, where the sails run perpendicular or square to the keel when in their neutral position. In this slide and the one that follows, there are some other traditionally rigged vessels to compare with. Notice the ketch and the yawl are also two-masted, but they are not schooners, because instead of the second mast being a foremast, they have a mizzen stepped aft of the main. Even though the vessel shown in the top left corner has some square sails on the foremast, she is still considered a schooner since her foremast rigging is fore and aft. The name of a traditionally rigged sailing vessel has little or nothing to do with the shape or material of the hull. If a bar of soap has 2 or more masts and is rigged fore and aft, then it is very much genuinely a schooner. These boats are sloops, by the way. Inland Seas carries only one gaff topsail, which is flown from the main topmast. Points of sail describe the basic way to trim sail depending on the wind direction relative to the boat. If the ship is pointed directly into the wind, the sails are flogging and actually working counter to propelling the ship forward. Under these conditions, we have little to no movement through the water, which in turn means little to no steerage. Basically, we have no control over the movement of the boat. We can call this in irons. Close hauled is the closest point of sail in which we can sail efficiently into the wind. If we steer any more upwind, we'll start to stall our sails and begin sailing more sideways than forward. Close reach is still sailing a bit to windward, but not as close to the wind as we could if we wanted to go close hauled. On a beam reach, the wind is hitting us directly on our side, or as we say, on our beam. A broad reach, we are sailing more downwind, but not directly downwind. If you're at the helm, the wind would be coming over one of your shoulders. Running, we would be sailing directly downwind. And notice the slightly different sail trim for each of the points of sail. The rudder, keel, and ballast all play a role in the way the sailing rig performs. Basically, the ballast keeps the boat upright, the keel keeps her from sailing sideways, and the rudder keeps her pointed in the direction you want to go. This is the rudder and lead ballast on inland seas. Before moving on, I need to give a brief explanation of what a vector is. Please read carefully, as this will help show the what and how regarding the forces involved in sailing. Notice the 20-pound force vector is 1/5 the length of the 100-pound vector. And notice how the 10-knot vector is 5 times the length of the 2-knot vector. This method of calculation helps illustrate how different forces or directional velocities combine or interact. This diagram illustrates with the use of vectors how the force of buoyancy and weight interact in order to keep the boat upright, and how the keel, by acting as a hydrofoil, creates horizontal lift to counter the horizontal force of the sails pushing the boat sideways. If you're interested in diving deeper into the physics of sailing, you can visit the website at the bottom of the slide. Daniel Bernoulli and Sir Isaac Newton are the two physicists most responsible for our understanding of the physical forces at work when sailing. When sailing downwind, it is a little easier to understand the physics involved. It's pretty much pure Newton. The force of the air hitting the sails pushes the boat downwind through the water. Creating a larger sail area by sheeting out and setting more sail will result in more air hitting the sails, thus increasing the force, thus making the boat sail faster. When sailing more to windward or close-hauled, the illustration of forces becomes a little more complex. In addition to Newton, Bernoulli starts to have a say in how these forces are created by the flow of air over the sails. The principles of how sail functions is basically the same as that of an airplane wing, since a sail is also an airfoil. It's just working vertically rather than horizontally. The boat here is on a port tack, but starboard tack works the same. It's just the mirror image. The mast divides the air, represented by the big red arrow, flowing over the port bow. The air flowing over the inboard side of the sail applies force to the sail as it is redirected. This force is best described by Newton's third law in that every action has an equal and opposite reaction. So when the air is deflected in one direction, the force in the sail deflecting the air is opposite that direction. Also, this air flows slower than the air flowing over the outboard side of the sail. If we were to apply Bernoulli's principle, the fast-moving air on the outboard side of the sail would exert less pressure than the slower air flowing on the inboard side of the sail. All of these forces over the entirety of the sail could be summed up into one vector showing the overall direction and magnitude of force the sail has on the boat. But notice the vector is not exactly pointed in the same direction that the boat should be traveling. Well, using geometry, if we were to break that vector down into two components, we'll hopefully get a better understanding of how this works. The first component of this vector is the force of the wind trying to push us sideways, or as we say, leeway. The force causing leeway is countered by the force of the keel against the water. The second component of our sail force vector is headway, and this force is countered mainly by friction of the water, which, if we minimize as much as possible, for example, by keeping our hull clean from marine growth, we will maximize our speed in the direction we wish to go. All of these forces over the entirety of the sail could be summed up into one vector showing the overall direction and magnitude of force the sail has on the boat. But notice the vector is not exactly pointed in the same direction that the boat should be traveling. Apparent versus true wind is the wind speed and direction that is blowing over the surface of the water versus what you feel when you are standing on the deck of a moving vessel. Let's say, for example, our vessel's heading is directly into a 10-knot wind. If the vessel is not making headway, then we will feel a 10-knot breeze coming directly over the bow. If we start making headway at, let's say, 5 knots of boat speed directly into the wind, then relative to the vessel, the wind will have increased by 5 knots. The sum of the true wind plus the artificial wind adds up to be an apparent wind of 15 knots, directly over the vessel's bow. If we turn downwind under the same conditions of 10 knots of true wind over the water, and the vessel is making a speed of 5 knots running directly downwind, relative to the vessel, an artificial wind of 5 knots will counter the true wind. Therefore, we subtract the boat speed of 5 knots from the true wind of 10 knots to give us 5 knots of apparent wind dead astern. Here's where the calculation can become a little more complicated, to where the use of vectors comes in handy. Let's say there's a 10-knot true wind at a right angle relative to the heading of the vessel, and the vessel is traveling at 10 knots through the water. By using the Pythagorean theorem and the vectors, we would expect our apparent wind to be coming over the port bow with a strength of approximately 14 knots. I do not expect you to be using vector trigonometry to figure out how to properly trim your sails. That would be a colossal waste of time and totally ridiculous. But I hope to give you some idea of how the wind speed and direction will change depending on the speed and heading of the vessel. So just keep in mind these basic points if you're working the foredeck and responsible for trimming sail. I hope you feel a lot smarter after this presentation, at least in regards to sailing. And keep in mind, Einstein was a sailor, but you don't need to be an Einstein to know how to sail.